And we're starting. So here we are for the next week of programming quantum computers. And we're going to be continuing with chapter 5. And Matt is going to pick it up where we left off last time. So take it away, Matt. And round of applause.
Sure. So first of all, there's not a whole lot left to go through. I know there were some good questions and ideas that were floated around last time. So I'll finish up the chapter, then we can open it up to whatever anyone discovered or thoughts they had since the last session. There isn't a whole lot. I didn't have as much time to work on my fancy animations. So, and I had, much to my chagrin, as I was putting things together, not the last night or two, I noticed most of the cool examples and items in the pictures he never actually modeled. So I didn't have a chance to figure it all out in my code and everything else. If you guys did and you want to share your screens later on, if you have those saved, that'd be great. But we'll walk through it. And again, we're kind of towards the end of this chapter. It's still some pretty exciting stuff. I'll definitely go ahead and share my screen again. Share that one and that one. Everything's going to do that. Okay. So you should be able to see my PowerPoint right now, and then also my internet on the side.
Yes, it's very wide.
Okay, sorry about that. How's that?
Yeah, no worries.
Okay, so yeah, this is just continuation on chapter 5. So the next thing he kind of gets into is encoding phase. And there was a couple really interesting things he talked about in this. And oh, I had the wrong animation there. Sorry about that. Yeah, there we go. So what he's talking about in this one is we're now going to change the phase. And it's like what we've already done. So I'm not going to rehash some of the older stuff too much. Again, we're seeing our same patterns as before. Going back, this was a similar example to what we had prior with this screen right here, where remember where we were altering a value of B based on where A was. And that was pretty neat to see. So now we're actually going to change the phase. And so what he's doing is says, well, let's change the phase where the value of A is less than 3 or greater than 6, and the value of B is 1. And so again, we're changing things based off of what our conditional values are. And again, this isn't really much different than traditional computation, but the cool thing is we're doing it in superposition. And so when we do that and you follow the code in the book, it's the same code we had before. And sorry, I don't have a screenshot of it, but basically where you can see them, in order to find out if A is less than 3, you literally subtract 3. And then remember, we look for that negative sign bit. And if it's negative, we knew it was less than 3 at the time. And then we, of course, look for if A is 1, and then if B is 1, and then we're going to flip it. And so what you actually see is that those 3 do change. And I modeled it in the animation only because I like to draw my boxes. It's a little easier to see when you do that. But they did have it in their quantum engine, which was kind of neat. And then you can actually see those phases change from the beginning to the end. Now you see the little circles flip, and again, that can drive your eyes a little nuts. But here we're actually, oh, I'm sorry about that. There we go. Here you can see we're actually decrementing by 3. We're flipping if A is less than 0. So again, we're looking at that sign bit. And then if B is 1, and then we're going to do that flip. And they call it a flip, and it's a phase flip. But you can see that all of our angles are now exactly 180 degrees. And this was an interesting notation, because this is the first time we've really made use of that color coding. And so it was kind of neat to see that color coding come out, and it's really obvious to see which bits were flipped. But again, having the boxes around it really helps out And so that's why I drew that in there. So the nice, interesting thing about this is he does make a point to say operations can also encode calculation relative phases. So this is, again, something we don't have with traditional bits. With traditional bits, they're either zeros or ones. Whatever your formula is and your end result, that's the result. That's it. You know, now we're used to finding out what the result is or what the result potentially may be just with our magnitudes. Okay, this may be a 3, it may be a 7. That's really kind of neat. We're able to kind of zero in on that quickly. But now we're actually encoding additional data into our results. So I found that kind of fascinating because it's like, okay, not only is it the magnitudes and what potential bits are left over, but now we have this other component, which is phase, built into our answer. And yeah, again, this is something normal bits can't do. It's either a 0 or a 1. You can't say, well, you're a 1, but you're also something, you're also blue, you know, if they wanted to figure out what they're going to put in their shopping cart or something. So that was kind of neat. The other statement that he kind of made was, it produces answers able to survive read operations. And this is where I was like, wait a minute, what the heck does that mean? Because this whole entire time we've been saying, once you read, you've destroyed the information. You are left with what you get. And so I'm kind of excited to see what that means exactly later on. He does say that being able to compute phases is definitely a core critical component of our library as quantum developers. And so that was kind of neat. The other, yeah, so that's kind of what I got out of that. Moving on, we start talking about reversibility and scratch qubits. So we normally can't do an absolute value because the absolute value of 4 and -4 are both 4. You can't reverse that because you are losing information. You're losing what that negative was. And so they say to get around this, we do it by using scratch qubits. And so you can see what they're doing there is we're actually gonna set the scratch qubit to 0. And then we're going to knot it based off that negative highest order bit there. And again, this all assumes we're dealing with negative and positive numbers. So that's our highest order bit. And then he makes the distinction to say, now remember, to negate something, and this was several slides ago from our last session, in order to change something from a positive into a negative or a negative into a positive, you knot it and then you add 1. So this first operation they do is they knot everything based on that scratch qubit. So if the highest order was high, if it was a 1, that means this is a negative number. So we're going to set our scratch qubit to 1. And then if it's a 1, we're going to knot everything and then we're going to add 1. And then remember, this little increasing set of knots is our standard add 1 or increment by 1. So this does give you the absolute value. And the fact that we're saving whether it was negative or not in that scratch qubit means that we can just reverse the entire procedure. We don't actually lose anything. And as we kind of talked about in the past, last session, reversibility doesn't seem to be a critical factor. And he does make a point later on that says, if you can't reverse something, it's not like you're going to get a QPU compiler runtime error. It's still going to work. It's just that you can't undo it. And what we're finding out with a lot, like if A is less than 3, well, let's subtract 3, evaluate A, and then re-add 3. It seems like a lot of the stuff that we're trying to do with our formulas is we have to put our qubits into a state, do some work on them, and then undo them. So I think that's where building a huge, healthy library of reversible operations allows us to be able to do a lot with what we're trying to work with. And so going on with that, we do see that our scratch bit is down the bottom. And as we step through it, your -3 becomes a +3, your -1 becomes a +1. Note that -4 remains unchanged. That's just how 2's complement works. It's how dealing with negative operations work. Again, if you're ever computing and you're at the extremes of your integer values, you probably need to increase your integer values. The idea that you're operating and doing math at those extremes is not a good idea. But so we see that work. The other fascinating thing is I thought, okay, well, you know, it's actually, you can see the numbers in that scratch qubit. You can actually see them in the 1. If they were negative, well, now they're a positive. As for a value, they're a 1 or a 3, a 0, 1, or a 3. But you actually see them in that scratch bit down below if they were 1. And I thought, well, that's kind of cool because you can visually see. We still know that those were originally negative values when we started off with them. The other statement he makes is keeping track of the original state with conventional bits require an exponentially vast number of bits. Yeah, so here we started off with 0, 1, 3, -4, -3, and -1. Well, you know, if you've ever tried to write an undo program where you have undo abilities, or like, what was my state beforehand? If I'm writing to a database and I need to keep that old state, you've got to have enough normal bits, normal information storage to track all that. Here we've kept track of 8 qubits with only the addition of 1 more bit, which is again pretty insane. It's little tidbits like this that I see every once in a while that I'm like, now this is starting to solidify more and more why quantum computing is so powerful. And it's going to kind of break open a lot of cool stuff that we're going to be able to do. So that was really interesting. So my thought was, okay, cool, scratch bits all over the place. Every time I need to do an operation, I'll just make a new scratch bit. And he even talks about later on when we're uncomputing. Oh, I got into digital. Sorry, so I don't have. We're going to do a lot of talking here, and then we'll go through the QC engine. But he talks about uncomputing and this idea that we'll use scratch bits, but you need to clear out your scratch bits in order to reuse them. Well, the problem is when you use a scratch bit, you've entangled it. And so, well, that's okay, let's just reverse the operation. Well, when you reverse the operation, you're technically destroying what you tried to do using your scratch bit in the first place. So he actually gets into some pretty neat concepts. He said, well, and if we're adding 2 numbers, A and B, and I apologize, I thought he had a thing for this, and yeah, this just gets into logic gates. We're going to do an operation adding A and B, but we need to know the absolute value of A first. Well, let's use a scratch bit on A. Let's do our addition of A and B, and then let's undo our scratch bit. So A itself is left alone. We haven't destroyed anything, but B has been altered, which is really cool. And so getting to use scratch bits, that becomes a pretty neat thing.
Yeah, and Matt, if you're interested, I actually did code up a bunch of the circuits.
Yes, I would love to see some of that, because I was talking through it and I realized there's some really great graphics and code that he's got in the book that I just didn't have time to put on paper because a lot of it he didn't have samples for. So yeah, would you want to cue that up?
Yeah. Do you want me to show that now, or do you want to loop back around?
If you've got something there, we can talk about it now. The last thing I'm going to talk about is his logic gates, and then just kind of my wrap up. So we're pretty much near the end. We ended with like only 4 or 5 pages left to go. Okay. Summary. So do you want to take control?
Yeah, I'll go ahead and share for this, and then we'll head back to you.
Yeah. I appreciate that, because I was really sad that I didn't have time to get this up and running.
Yeah, so I put the link into the chat for this particular MD file. This is in the repo that I've been putting my experiments in. And what I did was, for the pages that had diagrams but no code, I went and coded them up. So this experiment 5.5-7 is actually the one that Matt was just referring to, and actually have that in the QC engine right now. And so first of all, I wish there was a good way of the syntax being documented, because I need to change some of this code. So what I found out, I'll talk about the code and then we'll talk about the diagram. So these have a lot of C naughts with multiple conditions. And so like if we look at line 15, let's see, where are we? Absolute A. That is probably this step right here. So I'm C naughting this bit based on okay, actually no, that's not right. Oh yeah, it is. Okay, that one, and that one. Okay, yes, so it is. Now you'll notice that on line 15, I'm saying I'm C naughting 0x20, which corresponds to A0x2. And the reason I did this is because I didn't know there was a syntax for splitting out the A stuff individually. So what I found is that there's another syntax where you can say, and this is, I wish this was all documented, A dot bits 0x2 in this case. And so that would be the 0x2 bit on the A register. And theoretically, if I hit run program, it should be unchanged, which it appears this step is unchanged. So even though this code works, I kind of had to go, okay, 1, 2, 4, 8, 10, since we're in hex, 20, 40. And so that's what these numbers are, even though there's probably an easier way for me to do that. Okay, with that confusion, here is the circuit diagram that Matt was talking about, where we want to take the absolute value of A and add it to B. And so I put some values here. So for B, I put 0, 1, 0, which is a value of 2. Is that right? No, 3. It's value of 3. And for A, I put a value of
value of 2.
It's negative. Okay, I'm bad with this. Matt, what value is this?
Oh yeah, I'm gonna have to look that one up. I want to say that's
it's a negative. I intentionally did a negative number because I wanted to see the absolute value working.
Pulling it up here. Go ahead.
Are both registers 2 complements?
Yes, they are, but the negative bit
is
set for B. That's a -3? Okay. I will take your word for that. I know I did this intentionally. Okay. And so using the scratch bit, doing, I don't know that the circles do anything real interesting on this. Actually, there's probably too many of the circles because there's so many qubits in place. So here, A should have the absolute value of 3. And so then we do an add between B and the absolute value of A, currently what we have in the A qubits. And so then that should give us a, wait, did I do 3 plus 3 is 6?
No, it's you actually, B is right now set to 2.
Doing that wrong. B is set to 2. Yes, B is set to 2, and I'm adding 3, so it's 5. And so, yeah, okay. Apparently, I'm using 2's complement for A and just positive numbers for B in my in my adding. Oh, it's a good thing I know exactly what I was thinking when I did this. So then this adding of the B and the absolute value of A, and then undoing the absolute value of A, actually uncomputing it. So when we get to the end, A is in the same state it started in. So it's 1, 0, 1. So in my world, that's -3. And then B has now had 3 added to it. And if we're pretending that B does not have a signed bit, it's unsigned, then we took 2, we added 3, and we got a 5. Is that right?
That's perfect.
How does that look? And then the scratch bit is back to 0. And you know, like Matt mentioned, getting it back to 0, now we can use this scratch bit. The thing that I thought was interesting is it was saying, well, since it's entangled, if you read the scratch bit at any time, so let's read the scratch bit and reset it to 0, then that could potentially mess up the rest of your circuit. So I thought that was interesting.
And right here, since you set A and B to actual values rather than adding them, I think it's very deterministic. You're able to get what you get, you're looking for it. And if we
Yes,
were to read the scratch bit and destroy things, it's not a big deal. But it's when we start adding things and we have these potential values that becomes really important. Yeah.
Yeah, exactly. And I intentionally didn't had or phase anything because I wanted to see the bitwise operations in play and putting
Yeah.
things in place. So yeah, so that's what I did there. Any questions or comments on that?
The only quick comment I had is I noticed that I think there's an error on your first absolute value of A.
Oh,
Your first not, yeah, right there. Now I think we got lucky though. And it had
oh,
nothing
you
to
know
do
what? I messed this up right here, didn't I? This is the one I changed.
Oh,
Okay, so the line, apparently the line of code I was on is not the line of code I thought I was on. So that should actually be
yeah,
a
a 4.
4. I remember seeing something change in the
There we
corner of my eye. Apparently it was this one.
and that's phenomenal. I love that. Thanks so much. Because yeah, writing that out, I was like, last night, I was like, oh, shoot, I don't know if I have time to figure all this out. I had assumed he had already written it out. I don't know why.
Yeah, so let's see. So I think let's just try this before we leave. A dot bits. And so this is 1 and 4. Oh, but we also need, see, the other thing is we also need the scratch bit.
Oh, you need a scratch bit. Yeah.
Uh,
Is that possible?
I don't know if this will work or not. No, that did not work at all.
Yeah.
So maybe there isn't a good way of writing that out. In this case, since we're crossing between 2 separate registers. But yeah, I saw this somewhere and I'm like, oh, that's helpful. I should go change all my things. But then I started looking, I'm like, well, with the cross stuff, I don't know how that's going to work.
Yeah, and as I was putting my initial ones together earlier today, I was adding them all together. So I was using values like 15 or F instead of oring them together like you did. And I think the way you did it is much more intuitive by looking at it. Like if you just see, okay, I'm going to scratch it against F. What the heck is F? And then other times, you're scratching against 11 and 13 or something. And so I was like, wait a minute.
I want to remind you there's another literal way of representing a number. Is that's instead of hex OX, you do OB, which is binary, and then you just go positional. And if you have a fixed width font,
Oh, that's right.
it's kind of easy to see what bits are on and off.
So theoretically,
This is
JavaScript.
OB100 is 8, right?
Well, no, but we have to start at the top, right? So
Yeah.
Sure.
it would be
So if you're dealing with an 8, it
which
would be
way do we go? We
1
started at
0
the
0
top.
0 0. Yeah, you start with the highest order bit.
0 0 0 0.
So that'd be the same as your 8. Now it gets
Okay.
worse as you get into like hex 40.
But then I would go like this. Would that get, so is this the scratch bit?
I'll have to
The
look
highest order is closest to the B.
to the bottom.
Closest to the B or closest to the bottom?
Closest to the B. The B represents the
Oh, the closest to the, okay.
Biggest, 2
The
to
letter
the power
B.
of the biggest. Yeah.
The B in the representation, not the B register that we have on the circuit.
Sorry. Yeah.
Okay. Yes. Okay. So
And you're doing 4, right? Oh yeah. So yeah, you'd have your
this
based off your
maps-
B.
I'm going to click run and see if the circuit changes. Okay, the circuit changed.
Oh.
So what did you want to write? You wanted to write the
Oh,
So-
you got too many zeros.
I have too many zeros.
Yeah, because we only have 3 bits in the B register.
Oh, there's 3 in B. Okay. There we go. Okay.
Wow.
Yeah. Is that easier or harder? I don't know at this point. It's Jeremy,
Well,
would
what's
you prefer
easy
to
for
use
me-
hexadecimal or binary for this? I'm
What's
like,
easy for
well, I
me
would
is
prefer
I
not
can
to use
take these-
either.
I can take these bits and just mat them on the left.
Yeah, I
and
definitely
it's
see that,
done,
Nuri.
right? You just
Yeah.
take this and you go like this. Woo!
Tilt it sideways and line everything up.
Right.
Yeah, and I also noticed with some of my C knots when I was just working with like A, I just do A dot C knot, and then you can put your target bits in there,
Mhm.
and that helped.
Yeah, so
But
like
again,
line
if you're
line
standing
14.
outside, yeah, and you can do A dot C knot and then just scratch. It only takes one
Oh,
parameter.
yeah.
Rather than dealing with QC and dealing with the entire thing. It's pretty much the same. But yeah, I haven't experimented with how does that work when you're C-knotting A against something outside of A.
Yeah.
No, that's really cool. So yeah, getting back to what they were talking about in the book, here we put A into some state. We actually used it to affect B, and then we uncompute A. And what they were basically saying is, well, let's say you did want the absolute value of A, but you want your scratch bit back. Well, you can't get your scratch bit back without undoing what you did to A. You can't leave A in an absolute value of state and then reset your scratch bit to 0. You've just now put A into a state that's uncomputed, or you may have adverse effects. I'm not uncomputed, it's non-reversible, but you may have adverse effects. But they brought up this good point of, well, let's say you wanted to find the absolute value of A, not for A's sake, but so that you can use that against something else like B. And then we can uncompute A. And then we got our scratch bit back. And so, yeah, it's these little tricks that he's finding that it's like, okay, you may not do what you're trying to do right out the gate, but there may be a little side road you can take that gets you there. And I think a lot of what we're doing is finding out all these little tips and tricks to put in our tool belts. Moving on. Did you have the next one? 521? Figure 521?
Let's see. Is that a reversible?
Or 520? Yeah, your phase preservation.
Actually, yes, I do have phase preservation. Okay, so I was going to pass it back to you, but I'll pass it back to me.
Well, I'm having to talk over it.
Oh yeah, that's fine. I'd rather not talk about it because who knows what I was thinking when I wrote this. So just if you are looking through my repo, this is experiment 5-9. That's my experiment number, but generally I have where it came from. So this actually says figure 520. So let's see. Oh, does this thing work? Have I never used this before? Okay, I like that. Paste. Hey, that worked. Okay, so I will be glad to click wherever you would like me to click.
Oh, sure. So yeah, we can step through it like they do in the book. So if you go right after that, those hats, yeah, click right there. So let's see, what he was trying to do is we're going to alter the phase of only 2 of our bits. And the idea is that we're not going to change their magnitude at all. We're actually going to uncompute the whole thing. So this is where he's actually encoding the information into our end result without changing the bits themselves, the magnitude, which I thought, okay, now we're getting to something kind of weird and cool where he alluded to earlier. So right now we're saying, okay, all 3 of our A qubits are all equally likely, but we want to, for whatever reason, encode some value in just 2 of them. And normally all the way up through the book so far, we haven't really been messing with phases. So what we would do is we would do our operations in such a way that he's going to affect the end result of 1 and 7. what we would normally do is do our operations so that 1 and 7 would have a different magnitude than the rest. Typically, they would be the only ones left. They would be 50-50, one or the other. What we might be saying here is, no, all outcomes are equally likely, but each outcome may actually have different information. And so, not to get really basic, but end user might choose any one of 8 options, but options 1 and 7 have, for some reason, a different, maybe they're on sale, you know, choose 8 different colors right now. 1 and 7 are spring colors. We're in spring. We're going to give you 10% off. I'm just using a really terrible analogy, but the idea is we don't want to change the magnitude of these, but we still want to somehow encode something. And so again, we're going with this idea that we want to encode something if the absolute value of A is 1. And so if you want to skip after your absolute value of A, we've, oh yeah, that's right. We've taken our, and remember this is in 2's complement. So 4 is actually negative. 5, 6, and 7 are negative 3, 2, and 1. So those have all positioned. You can see they're now in that scratch bit, which is that lower option. So those were the negative values. And now we want to encode them if they're an absolute value of 1. So that second column where the top is a 1, that's what we're trying to affect. And so if you go just on the other side of, yeah, encode your Z, actually that whole little operation there, right there. Perfect. So now we've encoded, and again, I love this color coding. It's actually becoming really handy right here. So we've only changed those where the absolute value of A is 1. Now, if we leave it right here, we've kind of screwed up A a little bit, right? We need to uncompute what we did before. So if you go near the end, we're not going to read yet, but near the end, we've now uncomputed. All of the magnitudes are remain unchanged. And so this is the kind of the cool thing is so far we've been making all these magnitude changes to get what we want. But here we're not changing the magnitude at all. We've actually encoded additional information to those phases. So going back to my terrible earlier analogy, all 8 options for A are still up for grabs. They're all equally likely. But we've actually added some additional information into if the value is 1 or negative 1. And again, my terrible analogy, all 8 options are perfectly likely. We're trying to assess our customers. It's spring. Let's encode information. We're going to give them a 10% discount if they choose, you know, one or the other. Again, they're all equally likely. Let's see what the outcome of that is. And I'm sure there's much more scientific, better analogies, but I thought this was kind of cool because again, you can't do this with normal bits. Normal bits, you have to have a whole, almost an entirely duplicate set of data if you want to encode something without changing your original data. And so that's what he was kind of getting across here. Any other questions or examples behind that? Questions or thoughts or ideas? If not, no big deal.
I'm wondering if there's a way to, I know the HAD puts it in superposition, but I'm wondering if one of the QC engine ones can give us uneven odds. It seems to me the only representation is a 50%er, and it'd be nice to see if uncompute preserves magnitude or it just happens to be 50-50 and that looks the same, but isn't.
Well, I know in some of our prior operations, when we start getting to phases and HADs, we can actually change that. We've seen sometimes where one value is 20% and the other one's 80% magnitude. I don't have an idea off the top of my head how we can put this particular logic, but yeah, you're right. It would be interesting to say, well, is that preserved when we uncompute it?
Yeah, if there was a way to do a right with a probability and not just a right.
Where would you want him to put the right?
Well, on the initial setup or after the HADs. Like at some point before we start doing the absolute, we did a HAD on them.
Well, do you want to take the HAD off of one of those A bits?
No, because that wouldn't, what I want to see is a HAD that is not landing in landing in the 50-50 zone.
Okay.
That makes sense. Like there's a peak probability, but there's no poke probability. I want to have a circle that's a little bigger, you know?
Yeah, I can't remember off the top of my head. Does anyone know off the top of your head how we might make one of these circles bigger?
I think when we had that, there were phase operations involved. I don't remember exactly where they were. The chapter 6 is all about phase operations, so maybe there'll be more in there. Just kind of glancing through, it looks like in chapter 6 there are circles of different sizes in some of the circle diagrams.
But the phases are the angle.
Phases are the angle, and we're only seeing one of the phases.
Yeah, and we're seeing that successfully, right? That's the whole greenery. That's the whole thing, is that we basically said we're not messing with magnitude, only with orientation or the phase here.
And we've gotten our scratch cubic back also in this example.
Yeah, which is no biggie. I mean, all we have is a not, right? We have a not in the very first operation after writing a bit to it, a 0 in the beginning, and then we have a not at the end. All of the ifs, all of the tiny circles just means it's consulted, but it's not changing. So, yeah.
Yeah, no, that'd be interesting if, and maybe we'll see that in 6, and maybe that's some you can do over the next week and bring it back to the group. But that is interesting. If this would preserve, uncomputing would preserve the original differences in magnitude. So moving on, he starts talking about how we can actually use gates to replicate a lot of the operations we're doing. Let me pull up my thing again. Let's bring everything up. And thank you. This is absolutely awesome. So he gets into his gates, and he talks a lot about NOR gates and exclusive OR gates without really talking about what they are. If you've had this in the past, you might understand what they're doing. And so one of the things I went back to was to try and find, okay, let me see a refresher of gates and how all that works. And I did find one. Before I get to that, one interesting thing is this is actually how transistors and things and circuits work. They used to do all these things with actual transistors, and you had these inline circuits. And if you opened up an old Apple II computer way back in the day, you saw nothing but ICs or inline circuits all over the board. I mean, these boards were getting bigger and bigger, and it was simply because they couldn't fit enough gates into the board. And then we came up with modern transistors, and they're able to etch them all with lasers. And nowadays it's probably different, but I know back in the day when I was in school, and it's probably all changed now, but there was really only one gate on the entire CPU as far as the transistors go, because they realized that you could actually build your AND gates, your OR gates, your NORs, and all that stuff with one gate. And so once you figured that out, well, we don't need to build a board or a CPU with all these different kinds of gates, because sometimes we're going to need an AND, sometimes we're going to need an OR, and somehow tell the computer which one we're going to do. In an actual digital logic and applications, streetlights and other things, before they would put CPUs in some of these things, they were all gates. They were all logic gates, and you had to build your circuit. And that's one of the fun stories way back with Steve Jobs and Wozniak, is how do we build this arcade game and get as many few chips as we can get? And Wozniak figured it out. And of course, you know, the rest is history, and that's a lot of fun stories. But that's what they're talking about. How do we contrive this, our logic, into the fewest number of gates possible, and how do we do it in a way that's repeatable depending on what your goal is? And so he does talk about you can actually represent all the gates you need with one gate. And so he goes into some of what that means. In this particular one, I'm trying to remember because I'm flipping pages here, sorry. He doesn't have his label. Hold on, sorry. Feel free to jump in if you remember what he was proving on this one. Oh, these are his different things. So yeah, he's using this defoliate, and the defoliator is really just a NOT gate, but it operates on the AND of whatever bits you're looking at. And so what he's basically demonstrating, and he doesn't have labels here. He has them in comments, which is really funny. He's gone to great extents to put really nice labels and stuff throughout his code. But in this particular one, he chose to do it in comments, which is cool. But in our first gate, we start with C as being 0, and we're just going to simply NOT it. Okay, that's just a defoliate gate or a NOT gate that's not based on anything. We're going to NOT it every single time. And of course, when we read it, we get a 1. The one for the B context, what he's doing is saying, if B is 1, then you're going to NOT C. And again, that's exactly what he's got here. So we see B is 1, C is 0, and C is going to flip based on B. And so we actually see that when we read it, it was a 0, and now it's become a 1. If we really wanted to see, well, does it actually work? We can write our programs. B is 0, and you can see C is still a 0. It didn't change. Let me change it back. Actually, I think he redoes it down below. Here we're doing flip C based off of an AND of A and B. And so you can see he's starting to build some sort of these complex circuits. But if you want to get an idea of what these circuits are doing, I did find this digital logic primer. And I'll put this in the chat. There you go. It looks a little like it could use some sprucing up UI-wise, but what I love, it's actually all interactive. So he tells you right here, if you turn the switch on or not, the LED goes on or not, no big deal. And then he has what are called truth tables. So if you've seen digital logic gates and stuff in the past, we have what's called truth tables. You have your 2 inputs. You have your A and your B. They could be 0, 0, 0, 1, 1, 0, 1, 1, and then what's your output? And that really determines what the rules of the gate are. So this is our NOT gate, or he calls it an inverter gate. It basically just inverts, and this is the actual symbol that you'll see. And inverts. So right now the switch is 0, B 0, or sorry, our input 0. If we turn to 1, it changes back, it turns it off. And you can see here's his truth table right here. If the input's 0, the output's 1. If the input's 1, the output's 0. No big deal. You've got your AND gates. So we can turn either one of these on, it doesn't do anything, but if we turn both of them on, it does. Your OR gate, if it's an OR, if either one of them are high, they're both, it's going to light up. And now he gets into your fancy exclusive OR gates. And you can see he starts building these more complex gates based off of other gates. And you can see how they're starting to put this together. Now, oh, okay. So
It's
exclusive
interesting
OR.
that he's building it from a variety, because I thought there was a theorem that said they can all be built out of NANDs.
You're right. And yeah, so I'm not sure why he's building that way. But you're right. You can do them all out of NAND gates or not AND gates. It's an AND gate with a NOT. And that's actually this one. Oh, that's a NOR gate. Sorry. Where's our NAND gate? Right here. And so I don't have any of that information. Again, I kind of felt like this is a neat primer if you're interested in what those gates are doing. We don't have some of this logic, at least readily available in just our normal coding, unless you get into the bitwise logic libraries. The concept of an exclusive OR, I think, is really intriguing. Normally, I'm just going to OR things together. If any one of you are 1, then I'm happy. Let's move on. An AND makes sense. All of you have to be 1, and then I'll move on. An exclusive OR I like because it's like, okay, I've got 2 inputs, but I only care if you disagree. If one of you is a 1 and the other one's a 0, I care. If you both are 1, that's not what I'm looking for. And so there's some really kind of interesting questions that are in there as far as what you can do with it. But again, I kind of felt like, well, this is something everyone can dive into if they're interested. And this was a really neat resource because you can literally start clicking through it and playing with it and getting your mind wrapped around it. But kind of my notes around this was, he does say, notice that in some cases, in order to get your function, we need to add an extra scratch qubit. And so, okay, no big deal. We've already seen that. Let's add a whole bunch of them. Well, remember right now, the largest quantum computers have what, like 50 qubits that are sustainable, and they only sustain for a certain amount of time. A lot of people have been saying in order to get quantum computing to the place where it's really useful, we're going to have hundreds of thousands, if not millions of qubits, but we're not there right now. And so we can't just throw scratch qubits everywhere. We have to clean these things up. And so I kind of laughed and I was, yeah, he says one substantial challenge in quantum computation is reducing the number of scratch qubits needed to perform a specific computation. So again, we're back in that old Steve Jobs Wozniak thing. Okay, I want you to build me an arcade, but make it with the smallest number of bits, gates as possible, because back in the 70s, those gates cost money. And so it was literally more expensive the more gates you had. In the old, DOS days, we had the exact same problem. We had to fit everything into our initial 640K of RAM, right? And so I feel like we're in these interesting days where memory is scarce. So we as developers have to use a lot of cool tricks to make sure we're reusing and cleaning up after ourselves and making this available. So I was kind of chuckling because I thought, well, someday this won't be a constraint. We'll have enough qubits to work with. Someone behind, as developers, we'll just do operations all over the place, not realizing that someone else has already written a garbage collection library for our scratch qubits, and it'll start popping off our qubits that we're using, and we don't care, we don't know. Someone's gonna run through a quantum array that goes wild, and some hardware programmer is gonna come yell at them, this stuff doesn't grow on trees, you're using 1 million qubits underneath the covers, gotta watch out. But it'll be interesting. Yeah, what, 10, 20 years ago, people were saying memory isn't cheap. And now we're loading, 60 megs of libraries on the internet just to load an iPhone app, Well, maybe that'll be quantum computing someday. So that is the end of this chapter. So I kind of wrote to my notes in the end, do we really need to understand what's going on with these gates? I think it's fascinating. I think it's interesting. I don't know. Right now, I think we probably do need to learn it so that we can be very efficient with the way we're writing code. If you've got code that you need to write that needs to run on 1024 qubits and someone else figures how to run it under 256, well, then suddenly we're, a lot closer to be able to run that code on the hardware that we have. And then the other thing I thought, well, gates and digital logic, it kind of underpins everything we do. If you're doing event sourcing, in the cloud, well, what does all your subscribers look for? They're doing comparisons. They're saying, is this event on the line something I care about? Well, how do you know if you care about it? You're running it through some sort of comparison filter. Well, that's just gates on the back end. Theoretically, you're doing lots of ands and ors and figuring out whether this means anything. A lot of our digital logic. So it tests different development. That's nothing but getting an input and verifying if it's true and if it's what you expect. So the idea of gates, I think, are something that's valuable and something that we probably need to know. 5 years, I don't know, maybe we don't need to know that anymore. But that's pretty much the recap of that chapter. Interested in hearing anyone else's thoughts as we reach the end.
Yeah, that's very cool. Appreciate you putting this together, Matt, because that's awesome. Any other thoughts?
Have you guys seen gates before, at least at that level, or?
So I do not have a CS background, and I got a very interesting book called Code. Oh man, I can't remember who the author is. He's like really famous author guy. Let me see if I can find it real quick.
And while you're looking that up, I actually didn't have exposure to gates in my computer science degree. I had it in my electrical and computer engineering degree because I started out as electrical and computer engineer, and we were building physical digital circuits and working with CPUs and programming them. When I got to my CS days, we were talking more algorithms and compiler design and a lot of neat stuff, but a lot of my fellow students didn't understand what was actually physically happening underneath the covers. And so, yeah, I think a lot of CS grads may not have this either.
Yeah, it probably is more EE. So the book is called Code, The Hidden Language of Computer Hardware and Software by Charles Petzold. So it's a Petzold book, and it's really interesting because he talks about Braille, Morse code, kind of everything ones and zeros that kind of lead up to computing. And this is actually where I learned about gates, because he went through and showed like, okay, here's what the gates do. And I think he showed an 8-bit adder. And I was curious, and I was down at an electronics store and I saw these relays. I'm like, I should just buy a whole bunch of relays and try to build a physical 8-bit adder. I never did that, but I thought that would be really cool. So,
If you don't want to buy the physical one, you could use redstone
Yes.
inside Minecraft and build those very gates. Yeah.
Not quite the same.
I wanted to hear the relays clicking.
Oh, yeah.
Nothing like a real physical relay on a 480 volt line.
Some of those things are loud.
Oh yeah. I did some back in the day, some industrial control stuff as an electrician, and we built a wall for a disco and we had it with physical relays that it would go, and that thing was loud.
That's cool.
Not as loud as the music, but loud.
So I have one curiosity, just in case people are interested. Last time we talked about, anyway, here's the book on Amazon. We talked about what does the IBM quantum thing turn these into in transpiling. So I put one of the circuits into the IBM quantum composer. This is actually from the book. So this is code that was written by our authors. And this does the increment decrement. So the circuit diagram looks a little bit different because apparently the gates that IBM has only offers 2 conditions, whereas some of the gates needed 3 conditions on them for what ran in the QC engine. So it's a little bit different, but kind of has the same thing. I ran it, and here's what it got transpiled. Oh, and I will point out that there are barriers here. So I think Matt's the one that discovered that barriers mean, hey, don't optimize but across this line. So what's interesting is you can see the barrier here, and if I scroll in the transpiled circuit, this is the next barrier. So it took these gates, these 6 operations, and just ended up turning them into a whole bunch of operations. So the transpiling is kind of insane on this. And that's for people.
Well, but that's like saying that, IL is insane because C# or F# or whatever.
I can read IL.
Can you?
Yeah. It's actually.
Can you read a series of IL and say, oh, they're defining a function that goes over a loop and does a thingamabob to the lookup thing?
But there's just
learn-
two ways. Go ahead.
As I say, you just have to learn the language. It's readable once you understand it.
Yeah.
And the takeaway I have on this is I felt like we were pretty low level to what the qubit was doing. But it looks like IBM's, yeah, their conditionals have a restriction of, they're conditional only on one other bit, it looks like. So at least what the transpiled code looks like. So they have to go through these machinations just to come up. So we aren't nearly as close to the hardware level as I was led to believe.
Yeah, so
We've
that's
got some niceties.
the difference between assembly and microassembly, right? Like, I don't know if you did it in your microcontrollers, but the microcontroller code that runs the code that, does the half adder, something has to control that, right? Ad infinitum. You go smaller and smaller. And this is the, atomic element assembly. I was going, actually, when I was reading this, I was thinking the other way. It's like this open Q assembly or QC engine language is so clunky. For example, the way they did square is they actually blew up the square by saying we will, add so many times to create the multiplication, which when you think of it, what you want to do is you want to have a generative language that says square and then blow it up to the thing. And this might be what we're seeing here, is that in order to get the effect of the multiplication or higher order math, then we have to do a whole bunch of bit twiddling. And I'm thinking, this is nowhere near human useful language. We need a higher level language that says, I want an AND gate, do it for me, right? We want to, I don't know that we want to program in ANDs. We haven't gotten to real math, but certainly we can't have humans say, oh, we have two very large numbers, so let's just write out add, that's just not tenable.
Yeah, and one other thing I remember too, near the beginning of the book, or what we had talked about, I think Lynn brought this up, or Jeremy, quantum computers aren't going to replace traditional computers, but you're going to call out to them for parts of your routine, kind of like a GPU. If you're playing a video game, some of that code is running on your CPU, but it's calling out to the GPU for a lot of the rendering and other stuff, and now AI and things like that. Those GPUs back in the day were just matrix calculations based off of triangles and coordinates and things like that. Nowadays, you can say, build me a sphere, color it red, and have this sort of shading. But way back in the day, you had to tell those operations what you want it to do. And I think we're still in kind of that middle ground. And you're right, no one wants to write code that says do this and do this or. We want to write routines and functions and call out other functions and stuff. And eventually it'll write out whatever that is that our quantum computer is going to run on.
Right.
It'll be interesting.
Yeah, I guess that's kind of the DirectX. You don't get to say, high level primitives. What you get to do is say, here's my tessellated mesh. Here's the vector for the light source. Here's the thing, render frame. And I guess you're right. Our current programming, we're doing by hand what a higher order language should have done to set up this mesh of things and hand it over as a bunch of run this through your process qubit. But I still think we're doing imperative programming here, not declarative, right? If there was a way to say declaratively, I want to say there's a whole bunch of gates connected to each other, or there's a bunch of mathy things that hand over as an algorithm one to another. There needs to be patterns, higher order patterns like that, but you can just say, now pass it over the bus to the interface to the quantum computer and have it process it.
Sounds like Nuri is starting an open source project.
Yes.
Well, so far I managed to put a new line in the print on QC Engine, which nobody uses, and an F5 where you don't have to move the mouse. So
Yes, I love that. I need to play with it some more. And it's interesting that he'll note that certain things that you do in the QC Engine you can't do in the IBM.
Mhm.
And I wonder if the QC Engine is more of his way of saying, I'm building what might be the next ideal higher order. And right now I'm going to put operations in it that IBM can't do yet, and someday IBM may be able to do that. And then we'll have a new translation. But until the IBM or the other people can make this happen, there are things that we're probably able to write in QC Engine that just technically won't run on a real world.
Yeah, and I think the real world processors differ in their
Yeah.
capabilities as well. So this might just be like all the things that exist in some form somewhere, but yeah.
Yeah.
Yeah, I think he actually said that in the book, that the hardware itself varies in capability and in support for syntax. The barrier is an interesting thing where Jeremy was showing us there's a barrier. I was actually gonna jump in and ask, I wonder if the barrier negates the ability of this, or it's just for visualization. Because if there was no barrier and it optimized, it seems like whatever operation happened on the line would have happened. I would hope that the barrier is really saying that you shall not optimize, because if you optimize out based on what's happening on the line, you may get the wrong answer, meaning it's not just visual.
I think I remember reading somewhere, and I don't have it at my fingertips here, that the barrier did prevent some sort of optimization. In QC engine, it's just syntactic sugar, but in the IBM.
Right, because QC
And-
engine doesn't optimize. Yeah.
Yeah, and it's like anything, someone comes up with a caching library or a sorting library, and then one of us upstart programmers says, well, I don't want to do it that way. That's not the way I want to cache. Let me write it myself. So that's, I don't want IBM optimizing my thing this way. I know better. And so we'll stick barriers in to kind of help it out. And so, yeah, it's just,
I think it's in the logical realm. It's not in that. If you take away the time element, because when it's laid out graphically, you see the time element because you see that they're doing one operation per column. But if you collapse them and your line was affected by something in a previous column that modifies it later, when that collapses in, it changes the timeline. So I think it's on the logical. Still, it's not that IBM said our optimization is more volatile, so you need it. It's like in the abstract level of the language, you need to put that.
Okay, so about next week, chapter 6, I will ask for volunteers, but I will pass on some information that Lynn shared with me since she has read ahead. So next week's chapter 6 is amplitude amplification, which she says is pretty easy to understand. Chapter 7 is about Fourier transforms, which is more difficult. So do we have anyone who wants to jump in and say, I'll do chapter 6 so I don't have to do chapter 7?
I must admit that this week I tried to read ahead into even what Matt went over already, that I thought I understood when he said it, and I got kind of lost. Otherwise, so I'm concerned about presenting anything because I feel kind of lost.
Fair enough. Dan, any thoughts? I hate to put you on the spot, but feel free to say no. It's okay.
I'm just way behind on the reading, actually.
Mm.
Like I haven't even read 4 or 5. I got, once it got the teleportation and it said you need a computer, then I kept stop. I can't read anymore because I got to do it at a computer. But when I'm at a computer, I'm always doing something else. So I haven't got to that. So I don't know that.
Okay.
This is, how about, I guess I'll just volunteer to try, well, I don't know. In the format that Matt so aptly put things and stuff, I just feel like I won't be coming up with a presentation at that level.
So I will say that none of us should feel pressured to come up with a formal presentation. From kind of my impressions of what I want out of a book club is discussion. So if someone can lead a discussion on a topic, that is good enough for me. I don't need PowerPoint slides. So if it's just kind of like, okay, well, here's an example, let's talk about it. I'm okay with that. And if no one's comfortable with that, I'll be glad to pick up chapter 6.
And the other thing I would say is this last chapter with all the digital logic, it just kind of led itself to be easily documented. Not easily, I mean, it took some time, but in my head, it was a chapter I could literally start drawing and have it make sense to me. This is the first chapter that's been possible. The teleportation chapter, I mean, I remember one, I think Gerard was leading it, where we pretty much just dove right into code and started talking through the whole thing. And that was equally enjoyable too. In fact, I felt the chapter I went over, I was more talking rather than any of us discussing. And I like the discussion better. I think the chapter just lended itself to, well, let's look at lots of nice pictures. So I will definitely say, don't feel that that's the way to go. And I probably won't do it next time.
I'll give it a go with chapter 6. I'll just
Okay,
have
Dan.
to. I guess I could skip reading 4 and 5 since I'll just get back to those later.
Or you can or you can rewatch the videos, right? So everything's on YouTube. So
Yeah.
And
okay,
one
thank you,
thing-
Dan.
Yeah, one word of encouragement maybe for the group, and then you can repeat it back to me when I start getting discouraged. There are several times in this book already, I'm like, oh, if we're only in chapter 2 and I'm not getting it, wait, I'm going to be lost. And then you get to another chapter, or at least maybe a couple of pages, and you're like, that I get, that I understand what he's doing. And then 2 pages later, I'm lost again. So I guess I would say is, don't get stuck because you don't understand something and then wait till you understand it to keep going. Because we all may be stuck a long time if we all do that. So yeah, skip forward.
Yeah, and I've also found that as I've gone, it's like maybe it's the way the circle diagrams are working, and I'm kind of like, okay, I don't quite get it, but then kind of further down the line, I'll be like, oh, okay, I think I understand what that circle diagram was doing back in the last chapter. So sometimes we need more information, and again, I think that, you know, these authors are pretty brave to say, let's try to explain quantum computer programming to people who don't know quantum computers. So it's kind of, it is definitely a challenge all around.
All right.
Okay.
Great,
Well,
thanks.
yeah, thank you very much, Matt. And thank you for volunteering for next week, Dan. Matt, I just want to kind of reiterate what Lynn was saying last week. And she was telling me this morning, we had our regular weekly meeting, but she has a conflict right now. That she really appreciates the diagrams and things that you did, especially with the boxes, just to split out, here's how the bits work. That's something that I found very useful as well. So I know that, you know, we kind of all have different pieces that we can add to this, whether it's a walkthrough of code, or whether it's a diagram, or whether it's, you know, parsing through a circuit. So I think that's definitely a piece of value, is that we're all kind of understanding things a little bit differently. And so by kind of building on what everybody else is getting out of this, it's helping me understand things at a higher level. And so, you know, I think this is pretty awesome.
Yeah, this is fun. Cool.
Cool. Well, thank you very much. Matt, if you want to share your slides, feel free to drop them in Slack, and I'm sure Lynn will put them into the repo that she's been collecting. And we will see you all next week.
All right.
Have a good
Bye.
week.
You too.
Take care, everyone.